everyone, and welcome. Today, we're going to peel back the cover on two ideas that honestly run just about everything in our modern world: the simple but super powerful transformer and the really clever logic of control systems. Let's get into how these unseen engines really shape our lives. I mean, have you ever really thought about it? These things just work. It all comes down to managing power and managing processes. And yeah, on the surface, they sound like totally different things. But stick with me, and you'll see how they're basically two sides of the very same engineering coin. So here's our game plan. First, we'll dive into the device that literally tames electricity, the transformer. Then, we're going to pivot to the brains of the operation, control systems, and check out how we can describe pretty much any system out there using the language of math. All right, first up, transformers. You've probably seen these things in big green boxes in your neighborhood or up on utility poles. They are the absolute unsung heroes of the electrical grid. I'm not exaggerating when I say our entire power system just couldn't exist without them. Now, the key word to latch onto here is static. Think about that. Unlike a motor or an engine, a transformer has zero moving parts. None. It doesn't spin, it doesn't vibrate, there's nothing to wear out. It's just manipulating massive amounts of electrical energy using an invisible magnetic field. That's what makes it so mind-blowingly reliable and efficient. At its heart, you can think of a transformer as a kind of voltage translator. If it takes in a low voltage and spits out a high one, we call it a step-up transformer. That's what we use to send power hundreds of miles across the country. And if it does the opposite, takes in high voltage and gives out low voltage, it's a step-down transformer. You know, like the one that makes sure the power grid doesn't fry your laptop. So how in the world does it do this with no moving parts? Well, it's all based on this really elegant principle. An alternating current in that first coil creates a constantly changing magnetic field inside the iron core. It's that constant change, that magnetic pulse, that then creates a brand new current in the second coil. It's pure physics, transferring energy between two wires that never even touch. It's kind of magic. Okay, so that's the beautiful theory. But we all know the real world is a little messier, right? The clean concept on paper is never quite the same as the actual piece of hardware. So let's talk about the gap between the perfect idea and how these things actually perform. In a perfect world, a transformer would be 100% efficient. Every single watt of power you put in would come out the other side. But in reality, nope. The copper wires themselves have a little bit of resistance, which generates heat, and the iron core isn't a perfect magnetic conductor. All this means practical transformers always lose a little bit of energy along the way. So how do engineers figure out exactly what those real-world imperfections are? Well, they put the transformer through a whole battery of tests. For instance, an open circuit test helps them figure out the energy being lost in the core, while a short circuit test tells them about the losses in the copper windings. These tests are absolutely essential to know exactly how a transformer is going to behave out in the field. All right, let's totally switch gears. We've seen how a transformer is built to do one thing really well: maintain a specific voltage. But what about systems that need to constantly adapt to changing conditions? This is where we shift from just managing power to managing a process. Welcome to the world of control systems. When you get down to it, there are really two basic ways to control something. The first is an open-loop system. Think of your microwave. You tell it 2 minutes, and it runs for exactly 2 minutes. It doesn't care if your food is frozen or on fire, it just follows the command. Then you have a closed-loop system, like your home's thermostat. This is much smarter. It's constantly measuring the room temperature, the output, and uses that feedback to decide whether to turn the heat on or off. And here's the secret sauce that makes it work. You see that feedback path? The system measures its own output with a sensor. It then sends that information all the way back to the beginning to a comparator. That comparator's only job is to check for an error, the difference between what you want and what you actually have. That error signal is what tells the controller to make a change. That loop is the key to everything. But here's the thing. To design a good controller, you can't just guess. You have to first deeply understand the system you're trying to control. And to do that, you have to speak its language. And that language, my friends, is mathematics. Luckily, there's a systematic way to do this. You start with the real-world object. Then you use fundamental laws of physics, like Newton's laws, to write an equation that describes how it behaves over time. This gives you something called a differential equation. Now, because those can be a real pain to solve, we use a powerful math trick called the Laplace transform to turn that messy calculus into simple algebra. The whole goal is to boil the system's behavior down into one single elegant expression. And that final expression, that's the holy grail. It's called the transfer function. The best way to think about it is as the system's mathematical fingerprint. It tells an engineer exactly how that system will respond to any input you can imagine. It captures everything about its dynamic behavior in one compact ratio. This is the key that unlocks controller design. Okay, theory is great, but let's make this real. We're going to apply this exact modeling process to one of the most complex control systems out there, a massive power generator that's trying to keep the frequency of the entire electrical grid perfectly stable. So step one, we break it down into its pieces. We've got the generator itself making the power, a giant turbine spinning it, and a governor controlling the turbine. Now the whole challenge is that this system has to react instantly when a new load comes on, like say an entire city turning on their AC units at the same time. Next, we apply a law of physics. For something big and spinning, like a generator, we use Newton's second law for rotation. It's also called the swing equation. All it really says is that the generator's speed, its frequency, changes based on the difference between the mechanical power coming in from the turbine and the electrical power going out to the grid. And just like that, we have our starting point, a differential equation. Now, for the really clever move, working with those equations directly is tough. So engineers use the Laplace transform. Think of it like a mathematical cheat code. It translates the complicated calculus problem from the time domain into a much friendlier algebra problem in the S domain, which is way, way easier to solve. And finally, once our equations are simplified, we can make a separate transfer function for each component, one for the turbine, one for the generator, one for the load itself. Then we can just mathematically plug these blocks together to get one single final transfer function for the entire system. We've done it. We've gone from a real physical thing to a powerful mathematical model that can predict its behavior. And there you have it. We've looked at these two incredibly powerful ideas. Transformers are the muscle. They make sure the right amount of power is available. And control systems are the brains. They make sure that power is used intelligently to hit a specific goal, whether that's maintaining the temperature in your house or the frequency of an entire nation's grid. Which kind of leaves us with one last big thought. You know, in our world of smart grids, electric cars, and automated everything, these two fields are really starting to merge. The future isn't just about raw power or smart control. It's about the intelligent feedback loop that connects them both. Makes you wonder, what's coming next?